Joe here with another disc golf physics, or better, a disc golf math episode. I wanted to share with you a problem solving thing I've been doing. Um, we have an upcoming tournament at my disc golf course, Road Apple Disc Golf Course, and I wanted to mark some of the circles around the basket with some whisker markers. Got some online, and I saw them in videos and thought it would be a nice addition to the course. But I didn't know how many to get or how many to put around the circle or how far spread out they should be. Um, so this is my answer to all the people who in high school math were saying to their teacher, "I'm never going to use this. Why do I have to learn this?" Well, I got to use it. I use it for my job too, but I'm teaching physics. I actually get that question quite a bit too. But I used it on the disc golf course, and I thought I would share it with you. So I started off looking online for numbers of these to put around the circle, like how many per hole. And the only number I actually found somebody share was 8, and that didn't seem like enough. But I wanted to do the math to figure out how far apart they would be, and see if that was practical. When I bought them, I got 150 of them. So I'm kind of trying to figure out how to play with those numbers and see how many holes I can get with a reasonable number with a useful distance between them. Because if they're too far apart, you can't tell where the circle is. And if they're too close together, it's just too expensive. You can't afford that many markers. So how do we optimize that problem? So I did a little bit of math and I wanted to share it with you. So the goal here is to evenly space some number of markers around the 10 meter or just under 33 foot radius circle. So the distance from the middle of the circle out to the edge, that's called the radius. And we want to evenly space a certain number of markers. And I'm trying to figure out what the best number is to get them at a reasonable distance. Around the circumference, the circumference is the whole way around the circle. One time around the circle, one revolution or one circumference, means that I'm going through an angle around the circle of either 360 degrees to go one time around the circle, or 2 pi radians around the circle. To answer this problem, I needed to use the definition of what a radian is. So let's check that real quick. A radian is the distance around the circle, the angular distance around the circle, that creates an arc length on the outside that is equal to 1 radius. So if I go around my putting circle that has a radius of just under 33 feet, if I have gone 1 radian in arc length, then I will have created an arc length that is 33 feet. That's 1 radius. 33 feet apart, that would be too far apart. Plus, it doesn't actually divide out evenly because it's 2 times pi radians around the outside. To go all the way around the outside, you would have 2 times pi times the radius to go around the circumference. And that should actually make some sense, right? Because the circumference of a circle, the equation we learned in probably middle school, I suppose, is 2 times pi times r. That's where that equation comes from. But for our purposes, I looked up online how many markers people used, and so if this is our basket, that's my drawing of a disc golf basket. It's in the middle, and the circle is 33 feet away. The first thing I found said that they used 8 markers. Okay, so if you use 8 markers, then there are 8 spots, so 4 on each side. So maybe 1 there, 1 here, 1 here, 1 here. That means that each slice of this pie, each chunk that is created, is 1/8 of the entire circle. So it's 1/8 of the entire circle, but the entire circle is 2 pi radians. So I took 2 pi radians divided by 8 to get how much is one slice of the pie. And if I can figure out how many radians that is, that one slice of the pie, I can figure out how long this is, because 1 radian is equal to, the arc length is equal to the radius, or 33 feet. So all I would need to do is multiply by this answer right here, by the radius, which is, I'm rounding up, it's 32.8, I think, but I'm going to call it 32 feet. And that will give me the distance apart of those markers. So that's what I did. I opened up my calculator and I took 2 pi divided by 8, 2 pi being the entire circle, dividing it into 8 chunks, and found that each chunk was 0.785 radians around the circle. I took that 0.785 radians, multiplied by the radius, 33 feet, and found that the arc length, the distance between the markers, would be about 26 feet. And that seems to me to be too far apart. I don't think that's going to give you a good feel for the where the circle is, right? Like, am I actually inside? Am I actually outside? I don't think that actually helps. So instead, I thought, well, a clock is a circle. It's divided evenly. It's divided into 12 sections, 1 o'clock, 2 o'clock, 3 o'clock through 12 o'clock. And I said, well, maybe that would work. But I wanted to know the distance between them for that, so I did a similar process, but with 12 markers. So this time I divide my circle that is 2 pi radians around into 12 sections, and I got that each section is 0.52 radians. Multiply that by the radius to get the arc length. Now, I know, all right, so some people, if you're mathy, are going to tell me that I'm talking about the distance between these markers, which would be a straight line, but what I'm getting is the arc length, and those aren't going to be quite the same, but I think within a reasonable amount of error, it's giving me a good feel for how far apart they are. Also, the bigger the circle, the closer the straight line distance and the arc distance are, which is why, like, we're on a big circular thing, the Earth, the spherical thing. It's a curved surface, but we are so close to it, we're so zoomed in that it looks flat. It's a calculus thing. The closer you get, the more you zoom in, the closer the curve appears to be flat, the less it seems curved. So at 33 feet, it's given us a solid approximation. Okay, so that's way better, right? 17 feet, a little bit more than 17 feet in arc length across, versus just under 26 feet. Yeah, that's way better. But then I was thinking, I have 150 of these. That doesn't divide easily into with 12. So would it be better with 15? I know it'll be better, but is it worth doing? 15 does divide evenly with 150. So 150 divided by 15, I could do 10 holes. That would maximize the number of markers I can use with none left over. So how far apart should they be if I use 15? So same exact process, dividing my 2 pi radian circle into 15 chunks, getting the radians per chunk, multiplying the amount of radians per chunk times the radius to get the arc length per chunk, and we get it down to about 14 feet arc length between them, and using up all the markers that I bought across 10 holes on the course. So that's what we're going to go with. I'm going to give it a try. Let's go. I guess, trial is the only way to be sure how it's going to look, but that's the best we can do with what we've got and still get the maximum number of holes marked. So we're getting 10 holes marked at 15 markers per hole, and let's go see how it looks. All right, I'm out on the course. I've done 3 holes. I knew I was approximating with the arc length versus the straight line distance. So I knew I had to adjust, but actually I've learned most of the variability comes in the terrain. Like if there's a tree right in the way, or if the tree's blocking the sight, you want to make sure that it's not right behind it. So I found that a little bit less than my estimated value, which I expected, but not too much. We got them sticking out of the ground. It's fairly visible. I like it. It was tricky to distance them and get the distance of the basket. I was using my rangefinder and measuring from point to point, but it would help to have an extra set of hands. But otherwise, goes pretty fast, looks pretty good. I like it. So I went with 15. It looks like that's working pretty well. Obviously more would be better, they'd be closer together, but too many is expensive. So I think that's a good balance. But that's my disc golf course development math lesson. So hope you enjoyed it. I did. It was a fun problem to solve. So thanks for watching.